Pleasure to introduce Nate Wiggins from the University of Oklahoma, presenting on predictive modeling of transcatheter aortic valve replacement complications, empowering students in healthcare decision analysis. I pass the mic to you.
Sure. So I am Nate Wiggins. So this is called TAVR. So let's get started right away. So my medical school group is going to be John Byrne. He's at Harvard Medical School, and he's a long-term professor there. And then he also runs the HCA, which is Houston Healthcare Group, and it's one of the largest hospitals in the world. And he's the lead surgeon for open heart surgery. And then there's his team. Shelby DeRose is going to be a administrator. On the right, we have the students, University of Houston students I've got working with this, some of the data science and the math students. At University of Oklahoma, I have ISE and ELM, Industrial and Systems Engineering, and then Engineering Leadership and Management. And then we have the Harvard Medical School medical students working on gathering the data. So at the University of Oklahoma, I'm the director of ELM, Engineering Leadership and Management. We have these heavy project-based courses, data science and analytics, decision analysis, system requirements, and cost engineering. I try to get students major industry-driven projects in healthcare, finance, aerospace, and then oil and gas. And that way if a student wants to transition between industries, they're able to do that effectively. So this is going to be more on the medical side, although we're doing something with crypto next time. What is the STS? So this is Society of Thoracic Surgeon, and it's a group of thoracic surgeons. So a thoracic surgeon is a specialized surgeon at cardiovascular type, but there's different types depending on exactly what it is that you do. The STS algorithm, different hospitals have different versions of this algorithm. And so if you wanted your own version, how do you get it? Well, you chain an applied mathematician to a desk for about 6 months, and this is what you get. You get one of these. And so when you go into the hospital and we get all your information, your name, your birth date, your age, your gender, your race, any of your past complications, your family complications, all of that information, it's really different person to person, and that makes it hard to compare. So what we do is we put it all into this STS calculator, and so HCA has their own version. This is the STS official one online, and we put all this information in there. And out on the other side, we get a set of data that's the same, like normalized data for the different people. And these give us, it's the same set of categories. So even if I had different information about you as another person, the more I can get, the more accurate this is or better. And then these outputs, I go and I get these percentages. And so this will be like, for example, what's the percentage chance that you're going to have a long hospital stay after a major procedure? So if maybe you have all these different medical issues, then that's going to spike that value. So this is kind of built in so that this is easier on a HIPAA release. We do this because it's really hard to get like all that information about you, your name and your age, and we have way too much information. So to get that release is really hard. So with a HIPAA release and with we have to talk to the patient and, hey, we're doing these studies. Is it okay to use the data? So this is my Harvard medical students. They're doing, they're prepping you for surgery and they're talking to you about this. We're making sure that I can get this. So on the other side, my students are getting just these values, just these percentages, so they don't know anything really about the person. In the middle, there's a data science issue, and that's where my U of H students come in. I'm sending, I send them down there to do that because they're in the Houston region. So this STS database, we start looking at what models are there. Well, HCA has a model. It's a cabbage model. It's a coronary artery bypass graft. It's a pretty major open heart surgery. And so they have a model of this. It works pretty well. We can all argue about how we like their setup, but it works pretty well. Okay. As we look at the AVR, the MVR, we don't have existing models for that. And this will come up in a minute. And then TAVR, the one that we're looking at, and there's some hybrid surgeries that go on. So we want those as well. So there's a whole bunch of things that students can work on in the future. So you can see what I'm thinking and what Dr. Byrne is thinking. We need students. So we're starting to see this. And it's not like, oh my gosh, this one hospital figured this out. We started talking to the different health science centers at the different universities, and a bunch of those surgeons are saying, yes, 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 we want those models. So what is this TAVR? Well, it's a minimally invasive valve replacement, usually up through the leg, but it can come through different ways, and it's a catheter approach. It really, you usually go into a femoral artery or a similar type access point, and we go up to the heart valve for a replacement with an existing valve. The idea is that they have faster. So I'm sending you, think about this as a patient. I'm sending you in for this open heart surgery, and I'm telling you all this. Hey, we're going to go in. We're going to go in through a different vein. We're going to go up to your heart. We're going to change this out. Okay, what are you going to say? Is there any complications? I mean, you're thinking like a normal human here, worried about your results. Well, the hospital gets rated theoretically. Now, this has become a little bit fuzzy here. So on the cabbage model, we're able to do a pretty good rating, and we can demonstrate that HCA is one of your 3-star ratings. So what are we looking at? Well, we know that, okay, 1-star, 2-star, 3-star has to do with the standard deviations. So if I know that you're probably going to have a stroke during this procedure, and we do the procedure anyways, and you have a stroke, then it didn't necessarily go against me that you had a stroke. However, if we said you're not going to have a stroke, you're going to be fine, don't worry about it. Come on in, let's do surgery. And then you have a stroke, you either die or you have major medical complications afterward. Well, that's a problem. You might have a permanent pacemaker. This was supposed to relieve that issue, and now you're stuck with it. Or you might have an iliac stent or vascular ballooning, and that is as bad as it sounds. We're talking about balloon in a vein around that catheter usually. So what we're looking at then is we're trying to figure out, okay, were you expected to have a complication in this procedure? And did you have a complication? The ideal situation is that we can go through all of those different procedures and decide what's the best procedure for you as a person, right? Because of these probability. Now, this is going to be the best one theoretically. However, we are seeing issues with it. So this is something that we're worried about. Some of the challenges with modeling the data. Why can't we just throw it at somebody and get an answer? Well, it turns out that there's nonlinearity in the data. The STS data appear to be not directly linked to the output elements. The cabbage model was doing a much more effective job at taking those outputs from the STS and saying, okay, who's going to have which complication? The advances in technology have outpaced data collection to the point that we have data collection on PDFs and printed pieces of paper in the hospitals. And we have very advanced modeling methods available to us. So this isn't working. And then feature engineering complexity. We're going to talk about this a little bit, but there's a complexity in something called feature engineering. So I need smart math minds to be able to do this. When we start looking at the challenges with the data, some of them are related, some of them are unrelated. I don't have enough data. You know how hard it is to get that data out of a person? I'm telling you, you're going to have open heart surgery. And oh, by the way, I want this data for some math students or for some engineering students. You can see like skeptical, like, hold on, I'm going to do what now? So and not all that many people need this surgery. Okay. And I don't have like, I don't have a control data of like healthy people getting open heart surgery because they don't need it and it's really expensive. And so I don't have that data, which would be like really useful in modeling, but it's not like you're not going to sign up for that. So that's not going to work. And we have a large number of variables. Even that output of the STS is a lot of variables for the number of data. So we have an issue there. Okay, so standard statistical modeling is going to be a problem. Now, okay, so I have graduate students and I wanted to put them in this, but my graduate students, I work with the military and with aerospace groups. I have agreements, and my students are many of them are under specialized security clearances. So we decided not to put their names in this. So we're just going to say a graduate student. So I think some of you are undergraduates and you would love to have your name on this. This is like the opposite end of it, where we're producing stuff. And so imagine you're in aerospace, you're doing real hot stuff in medical. You might switch jobs here. You don't want your bosses to see this ability, and you also don't want everyone knowing that you're doing it. So because of your clearance, you may not be allowed. So what this is, so what we start doing is I start looking at, I don't have enough data, I want more. So we're going to look at each distribution, and we're also going to look at how data is related against one another. Then we're going to create synthetic data and lay it in there. Now, nobody trusts the synthetic data, but we're going to create it anyways for the training of the model. We'll come back to that. But we don't want, since you don't trust it, you can't use it for validation. You can't go and use synthetic data for validation. So we have to use real patient data for the validation part. We have too many variables, not enough data. We have a problem. We have too many variables to use something like sklearn or the H2O modeling. So if you go into like ChatGPT or Claude or Grok or one of these, and you're sitting here using it to generate code, the first thing it's going to want to do is use sklearn, right? A standard learning package. Then you go in to do it, and you're not getting the results you want. You're getting like a 70% accuracy, 50% accuracy. 50%, I could flip a coin and get a 50%. This isn't what I want. The H2O modeling has a problem of overfitting, and we'll come back to that, but that's another issue in itself. So synthetic data is not trusted. Nobody trusts in synthetic data, but you can't blame us for creating it. So let's hold on to that thought. The input values seem to fall into categories. We haven't handled this. So we're looking at like long hospital stay and short hospital stay is very different than like stroke and death, right? Those are different things. So we may need to categorize these. And any attempts to cheat on it, throw it through AI systems, something like that, gives you out things that look really good and don't work at all. That's a mini nightmare. So you'll sometimes we'll do something like this. Students will run back with these answers. Oh, it looks so good. And as soon as you start putting in test data, it doesn't work. So, and I have the hidden test data. So me and the doctor have hidden test data. So after you've run your model, you've tested against the test data, you turn it into me. Now it's time to play ball, right? Now we're going to test it against our test data to see how we're doing. Let's switch gears for a minute. What's a Black-Scholes model? It's an option pricing model. This is going to help us with option pricing and option probability. It's rooted in risk assessment. Risk is important here, especially on the doctor side. Let's talk about this for a moment. So we're looking at an options model. It's a second order differential equation. It looks not too bad. It is partial. However, it has a structure. Those of you that have taken it, I used to teach differential equations. Those of you that have seen this, it's probably not too bad. They were looking at an option. The price of the option is a function of the asset price and time t. This sigma here is the volatility of the underlying asset, and then R is a risk-free interest rate. If we take this and we do some, okay, so we're gonna set, we have two different situations, a call and a put. Let's talk cash secured. Okay, so a cash secured put means that like I'm gonna guess what the stock price is gonna be, and I get some money for that. Okay. And then let's say it doesn't reach my price. It's called a premium. I get to keep my premium. So I get to keep the money and I don't have to buy the stock. Now, if it reaches that price, I have to buy the stock for the price that we've agreed upon. And if it goes lower than that, then I'm not getting a great deal on the purchase, but I got it. So that's called a cash secured put. Now, let's say I bought the stock. I don't really want the stock. So what I'm going to do is called a call, a covered call. So I'm going to guess the price, or I'm going to select the price that I want to sell it at. Again, I collect a premium. If it reaches that price, then I have to sell it. If it goes above that, I don't get that extra money. Somebody else does. I don't know how that works, but I don't get the premium. I just get whatever I said I was going to sell it at. If it doesn't reach that price, I get to keep the premium and I keep the stock. So depending on if you want to buy the stock or you don't want to buy the stock, if you want to keep the stock or you don't want to keep the stock, you can do calls and puts and play this game. If we do a substitution where we let this kind of volatility, and then we set X to ln of the S, which again, remember back here is the asset price, right, is going to be, and so V is the price of the option at asset price S. So we do these substitutions here, and then we do some algebra. I'm not going to do the algebra for you, and we end up with a heat equation. Okay, so this is, if you heard of a thing in mathematics called isomorphism, being able to transform one thing into another, kind of from smooth transformations, that's what we get as a heat equation. If we solve the heat equation with a closed form solution using normal, it's a normal distribution. We use a cumulative distribution function for a normal distribution. Then we can get these call and put options. We're only going to consider the call option here, but we end up with actually a closed form solution. This has a few assumptions here, but this will be fine for a moment. I don't know if you've ever seen this. Okay, let's focus on the call option. The call option works like this. That first term is an outcome or a benefit. The second term is related to risk. So we're taking the outcomes minus the risk. Let's go and consider this in kind of a feature engineering format. We have a treatment outcome minus a treatment risk. So now I'm going to take all those categories that we were getting from the STS, and I'm going to revise them. I'm going to rewrite them in a way that I have this categorization of risk. Those are going to be renal failure, stroke, or mortalities, right? So those are major. And then the outcomes are going to be, well, you might be on ventilation. You might be in the hospital for a little while or a long while, or we might need to do a reoperation. So we've categorized these in different ways, and we're going to utilize them across a covered call option. Why? Because you already own your body. We're going to look at variable reduction and relationships and how we can do some of that. And so what we're going to do is we take the treatment outcome minus the treatment risk, and we take this. So I have basically what I do is I run a correlation matrix of all the variables against the other variables. So along the diagonal, you'll see it's perfect. All of those are exactly one, because if you check something against itself, it's going to be perfect. Now, long hospital stay and short hospital stay, for example, are going to be inversely related, right? If we expect you to have a long hospital stay, we probably don't expect a short hospital stay. So there's a way to set up some mathematical relationships there. So there's an infrastructure for us to look at the correlations between these, start relating the variables, then set them up in the call option format. From there, we can look at, well, if C is greater than 0, the treatment is greater than the risk, and if C is less than 0, then the risk is greater than the outcome. For each patient now, we have a value C that we can apply by applying their values from the output of the STS model and going through a feature engineering so that we only have one value of C that represents this person. We then can put that with stroke, permanent pacemaker. So I make a relationship in that way. So I've used my differential equation to help me set up a feature engineering format that we're going to use as a variable reduction. Some of the major results that we get from this. Trying this with the sklearn package, a standard learn package, gets you a 94% performance, precision of 89%. That's good, not good enough for the medical industry. So good. Sorry, I have notifications. So we have H2O package. We have it gives pretty good results. However, we're running a risk of overfitting, and we're seeing the overfitting start occurring. So we're very concerned about that. Let's move across. These things don't happen often so usually these are pretty successful, particularly with the group of surgeons that I'm working with. They are some of the best surgeons in the world. So when you're going in for surgery, I mean, you really want this guy if you can get him, or his staff, right? They're amazing. So let's say this happens. Well, then it's rare event. Possibly those standard learning packages are not appropriate. We need to go to a neural network type spiking. We're looking more at a Hoskin-Hutchley. If you hadn't looked up those set of differential equations, it might be worth just playing around a little bit on it. With the MATLAB packages, actually, these can solve those. That was one of the major events of MATLAB back in the day. We can put this in, and we start looking at this through different gradients, and we start running these. We want to see false positives is what we're after. False positives, false negatives. I want to see when I'm wrong, how I'm wrong. I want to be able to run it under a confusion matrix. I want to be able to start figuring this out on a more optimized scale. We see that gradient boosted have lower sensitivity. They have medium level of misclassifications. We like things with lower sensitivity if possible. However, we want the lowest number of misclassifications. The hybrid ADAB in the neural network performs the best. It's an ADA boost, and it really runs best in terms of lower classifications. So we end up using, again, a different type of sklearn is more of a standard transformer network. The neural spiking is going to be a lot more complicated to implement. So again, I need somebody that's not going to be overwhelmed by the mathematics. We see this as an effective method of handling this type of rare event. So this modeling type may be applicable to other areas. And that's why I'm going to go over. I don't want to do stocks and bonds because I have some students employed in the financial sector, so we can't do that. So we're going to go after crypto. I'm going to use MathCoin just because I feel like that's an appropriate one for these classes, right? But we're gonna start looking at freak spikes, freak crashes, things like that. Same idea though, and it's going to run out of these neural spikes. So this has a ton of potential. So some of the conclusions, we see the decision analysis project demonstrates a method of creating a decision support system for medical usage. Additionally, I see that I can quickly train students to create these type of decision support systems, and we can do very advanced ones if they come in with math skills. So I'm heavily recruiting from math departments, particularly once you get a job and we're pulling out of your job benefits for school so you're not paying for it. Intellectual merit. This shows a method for order reduction on machine learning. And this is highly effective, not only in the medical industry, but we're seeing this effective in other places. This has a lot of potential. I'm a consultant in the oil and gas sector, and this has a lot of potential. I will tell you that. The broader impact is that this has potential to impact thousands of at-risk patients each year if it's implemented correctly. We can find out very quickly, hey, I'm worried about you having ballooning in your veins, or I'm worried about you having a stroke. If we move forward with this technique, I don't think it's for you. I know it's the most state of the art. Let's move you over to a different method. So understanding that you might have an issue that maybe we didn't catch early on you know, that could trigger this. Okay, so that's another one. And we see that this needs refined. There's ample opportunities for publication, particularly some of my students aren't able to publish because of their security clearances and different things. That means that there's a big opportunity here for students to get involved and to create these, to publish these, and to present these at conferences like this. Okay, and I am regularly helping students. I have students at 4 universities and senior design projects. I have master's projects at 2 different universities. We have students all over the place that we're working together. I've got companies from NASA, from oil and gas, and from the medical and financial sectors very interested in students like yourself. So there's a lot of opportunity to move forward with these types of models. This is my contact information. You're welcome to contact me anytime you need. I appreciate the opportunity to present with y'all, and I'm open to questions.